Hi again, Science 9. So here, as promised, I've got a quick lesson for you on the topic of the greenhouse effect. This relates to the cycles because the greenhouse effect takes place in the atmosphere, and you're also going to see as we go into the cycles a bit more, how it relates to the water cycle and to the carbon cycle and to the nitrogen cycle. It's all interconnected. If you've ever been inside a greenhouse and you know a bit about the greenhouse effect, you'll kind of understand the connection. When you go inside a greenhouse on a summer's day, or any day really, you're going to notice it's warmer than outside, which maybe is a bit counterintuitive. The walls are made of glass, there's no insulation, there's no heat source, and yet somehow it's warmer inside the greenhouse. This has to do with what the greenhouse does with the radiation that goes inside it, because after all, of course, it is made of glass. In order to understand this topic a bit better, what is often done is people start talking about Earth's temperature equilibrium, the energy balance of the Earth. Now on Earth we have a number of energy sources. Of course, there's the core of the Earth, which is molten metal, super hot metal, like a solid. It's always slowly shedding that heat off into space, but that's a very slow process. Most of the temperature that we experience as heat here on the surface of the planet, in nature, it comes from the sun. Now that being said, if we were always getting new energy from the sun, and over time it was just accumulating here on Earth, well then before long the atmosphere would be hot as an oven. What instead we have happen is a temperature balance where over time the amount of energy coming in from the sun is all eventually re-radiated back into space. That being said, some energy does stay behind to heat up the atmosphere, to heat up the Earth before it's then re-radiated to space. Often what's done to understand this better is to use a kind of an imaginary situation where we have 100 units of sunlight. And we'll just call them, well, if it's 100, we're talking about percentages. A unit of sunlight could be like a particle of sunlight or a photon or something like that. Point is, I'm saying there's 100. Now, of those 100, well, in general, what can happen to light when it strikes the Earth, when it comes towards the Earth? One of two things can happen. One, it can be reflected. Two, it can be absorbed. If the light energy is absorbed by something, what that means is that the energy from the light is being taken in and it can increase its temperature. If it's reflected, then that light goes right back into space exactly as it came in. Now, of a reflection, here I'm going to zero in a little bit on that diagram I showed you. First of all, this black line right here is the Earth's surface. Obviously, these here are clouds. First three possibilities are this. Here's the sun, the red circle. First possibility is that it's reflected by what are called aerosols. These are very small particles that are in the atmosphere. Smoke is an aerosol. Smoke can reflect light back into space. Before it even reaches a cloud, before it reaches the ground, these particles of smoke or dust, small solid items that are high in the atmosphere, can reflect atmospheric radiation, the sun's rays back. Also, clouds can, of course, reflect the sunlight. I mean, after all, they are white, and we know that being white tells us that they're reflecting a lot of light. And lastly, that sunlight can strike the surface of the Earth, but still be reflected. In fact, the way it breaks down is that of our 100 units, 31 get reflected back into space exactly as they arrived. No change. They haven't been absorbed. The remaining 69, however, are absorbed before they're what's called re-radiated. Here's how that plays out. Some energy will be absorbed by the surface of the earth, as you or I experience when we're walking around on a sunny day and we feel warmer because the sun is striking us. Some of it is actually absorbed by the atmosphere, the gases in the atmosphere, and some of it is absorbed by clouds. Now, all of that is eventually re-radiated back into space. How? We know that hot air doesn't get into space. What's actually happening is what's called longer wavelength radiation, called infrared radiation. It's kind of red, but it's even longer wavelength, so you can't see it. Remember in grade 8, they talked about the electromagnetic spectrum. That's the language I'm using here. The infrared radiation is what we associate with things that are warm. Something that is warm gives off infrared radiation. If you've ever seen those night goggles that sometimes soldiers will wear when they're for fighting at night, the way they work is by seeing the infrared wavelengths of light. So when you're using your night vision goggles, you can see people walking around because people are sources of infrared radiation. Anything that has heat is a source of infrared radiation. And that infrared radiation, having been absorbed as sunlight, is then re-radiated back into space. But here's the deal. I'm not going to go into all the details here that I could, but I do want you to know this. Some of that re-radiated infrared radiation, right, gets reabsorbed by the atmosphere. So let's go through that again. Sun's rays, a unit of the sunlight strikes the earth. The earth absorbs that energy, but then re-radiates it as infrared radiation. That infrared radiation, some of it goes right back into space, but some of it, about 15% from your starting 100, is absorbed by the atmosphere. This, in a nutshell, is where climate change comes in. Because there are certain gases that can do this and certain gases that can't. Nitrogen doesn't. Oxygen doesn't. These are the gases that make up most of the atmosphere. But two gases that are very important have that property. One is carbon dioxide gas. Two is water vapor. So again, what they can do is for your sun's light that has struck the surface of the earth, warmed up the surface of the surface of the earth re-radiates that as infrared radiation. Some of it goes into space, but about 15% from your starting 100 is absorbed before it can get back into space. That is the greenhouse effect, is that reabsorption of infrared radiation that would otherwise escape into space. And that greenhouse effect is responsible for much of the heat that we experience in the atmosphere. The fact that the air is so warm as it is due to the greenhouse effect, which is because we have an atmosphere. If you go, for example, onto the surface of the moon, the average temperature of the moon is, I can't remember the figure. It's about freezing. You can't live there, of course, because there's no air, but the moon is that cold because it has no greenhouse effect. It's the same distance from the sun, so that's not any different. The difference is accounted for by the fact that there is no atmosphere on the moon, but there is one here on Earth. And because we have a greenhouse effect, that allows temperatures to be as warm as they are. The problem gets to be when there's too much of those gases to maintain our current conditions as we experience them today on Earth. And we get into situations where those gases are at a level not seen for millions of years. And this is where the discussion of climate change and our role as humans comes in. I'm just going to zero in on some of the other topics from here and also parts of the diagram and then show you what I wrote here. So I have these arrows right here. Arrows 1, reflection by aerosols. 2, reflection by clouds. 3, reflection by the ground. Remember, that radiation never got absorbed. It just went right back into space. And then here we have our other possibilities for that radiation being absorbed by the surface of the Earth. 5, it's absorbed by the atmosphere. 6, it's absorbed by clouds. Now remember, and here's, it all eventually ends up going back to space, but some of it sticks around enough to warm up the atmosphere. And here, this is an example, this is a case where we've got energy that has been absorbed from sunlight, is re-radiated as infrared radiation, but before it can get into space, is reabsorbed by gases in the atmosphere, greenhouse gases. And oh yeah, here's how the numbers break down, by the way. This is your 31, the reflection, and the 69, absorption by atmosphere, clouds, and surface. There's more to the diagram that I will teach you when you take Science 10. I hope you found this useful, and talk to you soon.